Look up at the night sky, past the familiar constellations, and buried within the sword of Orion lies something extraordinary, a swirling sea of stars and gas so vast, so alive with mystery, it feels almost like the universe is whispering secrets just out of reach. This is the Orion Nebula, a cosmic nursery where new stars are born, where colossal pillars of dust twist into shapes that defy imagination, and where phenomena so strange, so utterly baffling, they challenge everything we think we know about space. Imagine a place where temperatures swing from freezing voids to searing infernos, where newborn stars blast away their own cradles of gas, and where shadows dance in ways that shouldn't be possible. This isn't just a nebula, it's a theater of the cosmos performing wonders we're only beginning to understand, and today we're stepping into that theater. We're about to unravel 30 of the most bizarre, mind-bending phenomena hidden within the Orion Nebula, each one more astonishing than the last, from rogue planets drifting untethered through the chaos to freakish stellar tantrums that rip through the fabric of space itself. These aren't just scientific curiosities, they're clues. Clues about how stars are born, how planets form, and maybe even how life itself could emerge in the universe. The Orion Nebula isn't just a pretty picture, it's a puzzle, and every strange glow, every unexplained flicker, is a piece waiting to be placed. But here's what's truly thrilling. This nebula isn't some distant abstraction. It's close enough, just 1,300 light-years away, that its light reaches us as it was when empires rose and fell on Earth. When you gaze at it, you're looking into a mirror of cosmic time, watching processes that shaped our own solar system, and that's why these 30 mysteries matter. They're not just quirks of space, they're part of our story, so buckle up. By the end of this journey, you won't just see the Orion Nebula differently, you'll see the universe differently. Because out there, in that shimmering cloud of gas and starlight, the impossible is just another Tuesday. Deep within the heart of the Orion Nebula, a group of young stars known as the Trapezium Cluster is tearing up the cosmic rulebook. These aren't your typical, well-behaved stars moving in predictable orbits. They're more like reckless teenagers in a gravitational mosh pit, shoving each other around with enough force to leave astronomers scratching their heads. At the center of this stellar chaos, 4 brilliant stars dominate the scene, their light so intense it carves out cavities in the surrounding gas, but their orbits, they're anything but stable. Recent high-resolution observations have revealed something astonishing. These stars aren't following the serene, elliptical paths we'd expect. Instead, they're locked in a violent game of celestial bumper cars, their trajectories zigzagging unpredictably as they yank each other around with gravity's invisible ropes. One star might suddenly lurch inward, only to be flung back out by the combined pull of its siblings. Another could spiral dangerously close to a neighbor, their mutual attraction warping space-time like a trampoline stretched to its limit. What makes this even stranger is that our current models of star clusters just can't fully explain it. Supercomputer simulations struggle to recreate the sheer pandemonium playing out in real time. Some scientists suspect hidden, unseen objects, rogue planets, or even failed stars might be stirring the pot, their gravitational nudges amplifying the chaos. Others think magnetic fields threading through the nebula could be yanking on the stars like puppet strings. But here's the wildest part: this instability isn't just a spectacle. It's a cosmic laboratory. By watching these stars misbehave, we're getting front-row seats to the messy, violent process of how star clusters evolve. Some of these stars might eventually get ejected entirely, doomed to wander the galaxy as interstellar orphans. Others could spiral into catastrophic collisions, triggering outbursts of energy visible across the cosmos. The Trapezium Cluster isn't just breaking rules, it's rewriting them, showing us that the universe's nursery is far rowdier than we ever imagined. If the Trapezium Cluster is a mosh pit of unruly stars, then the Herbig-Haro objects scattered through the Orion Nebula are the neon-lit graffiti they've spray-painted across the cosmos. Among them, one stands out like a celestial whirlwind, a structure so bizarre, astronomers nicknamed it the cosmic tornado. Picture this, a twisting, luminous funnel stretching trillions of miles through space, its tendrils glowing with the violence of a stellar birth. This isn't just another pretty nebula feature, it's a shockwave in slow motion, carving its way through the universe like a blowtorch through fog. This tornado isn't made of wind or dust, it's a Herbig-Haro object, a cosmic jet blasted into existence by a newborn star hidden deep within the nebula's gas clouds. As the fledgling star spins wildly, it shoots out twin beams of superheated particles at speeds topping 1 million miles per hour. These jets slam into the surrounding gas like a fire hose hitting a wall, creating glowing arcs and ripples that stretch for light years. Hubble's razor-sharp images reveal the structure in eerie detail, braided filaments, knotted loops, and eerie blue-green hues fluorescing as charged particles collide. But here's where it gets truly strange. Most Herbig-Haro jets shoot out in straight lines, yet this one corkscrews violently, as if the star itself is wobbling like a spinning top. Some theorists think an unseen companion star might be yanking it off kilter, its gravity warping the jets into this twisted masterpiece. Others speculate magnetic fields are to blame, contorting the outflow like taffy. Whatever the cause, the result is a celestial paradox, a structure born from chaos, yet so precise it looks sculpted, and the implications are staggering. These jets aren't just cosmic fireworks, they're delivery systems, hurling heavy elements forged in stellar cores out into the nebula. The same carbon, oxygen, and iron that might one day form planets or even life. Every twist in that tornado is a brushstroke in a larger picture. The Orion Nebula isn't just creating stars, it's seeding future worlds with the ingredients of everything we know. Amid the swirling chaos of the Orion Nebula, a structure so sharply defined it looks almost artificial cuts through the glowing haze, the Orion Bar. This glowing blade of gas and dust stretching over 2 light years long isn't just a pretty backdrop. It's a cosmic frontier where the rules of chemistry and physics twist into something unrecognizable, a place where molecules dissolve and reform under a relentless barrage of radiation. At first glance, it appears like a simple boundary, a wall where the nebula's bright core meets cooler, darker clouds, but peer closer, and the bar reveals itself as one of the most chemically bizarre environments in the known universe. What makes this feature so puzzling? It's a pressure cooker of contradictions. On one side, the Trapezium Cluster's stars blast the bar with ultraviolet radiation so intense it shreds molecules apart. On the other, vast reserves of cold gas and dust resist the onslaught, creating a bizarre transition zone where destruction and creation happen side by side. Here, common compounds like carbon monoxide don't stand a chance, they're torn to pieces. Yet, against all odds, astronomers have detected complex organic molecules clinging to existence, including acetone, ethanol, and even precursors to amino acids. It's as if the bar is a cosmic distillery, brewing ingredients for life in the harshest possible conditions. The real mystery lies in how the bar shapes star formation. Some researchers argue it acts like a shield, its dense layers protecting pockets of gas long enough for gravity to pull them into new stars. Others see it as a catalyst, its turbulent chemistry actually accelerating stellar births by compressing gas into critical densities. Then there's the radiation problem. The bar glows far brighter than our best models predict, suggesting hidden processes we haven't yet grasped. Some speculate tiny, unseen nanodiamonds or rogue electrical currents could be amplifying the light, turning the bar into a celestial neon sign. One thing's certain, the Orion Bar defies simple explanations. It's a laboratory where the universe tests the limits of matter, proving that even in the most hostile corners of space, the building blocks of existence find a way to endure and perhaps to begin anew. Nestled within the Orion Nebula's glowing embrace, hundreds of tiny, swirling disks, each no larger than our solar system, hold the secrets of worlds yet to be born. These are the Proplyds, short for protoplanetary disks, and they're some of the most breathtaking and tragic objects in the cosmos. Picture a whirlpool of gas and dust, dense enough to blot out starlight at its center, where a fledgling star greedily pulls material inward. Around it, particles collide and stick together, slowly growing from grains of sand to boulders, then to planets. It's the recipe for solar systems playing out in real time. But here's the twist. In the Orion Nebula, many of these infant systems are fighting for survival against an invisible enemy, radiation so fierce, it's literally blowing them apart. The Hubble Space Telescope has captured Proplyds in staggering detail, revealing shapes that defy expectations. Some resemble comets with long, glowing tails streaming behind them like cosmic windsocks. Others look like bullseyes, their outer edges shimmering as ultraviolet light from nearby massive stars scorches their surfaces. The most heartbreaking are the teardrop Proplyds. Their once pristine disks stretched and warped, their material evaporating into space at rates that would vaporize Earth's oceans in seconds. These aren't just abstract shapes, they're solar systems in their infancy, some doomed before they ever get the chance to form planets. The culprit, the Trapezium Cluster's colossal stars, pumping out enough UV radiation to ionize entire swaths of the nebula. For Proplyds caught in the crossfire, it's like standing in front of a cosmic blowtorch. The radiation strips away their outer layers, creating immense pressure that can halt planet formation entirely. In some cases, the disks are evaporating so quickly, astronomers can practically watch them shrink over mere decades, a blink of an eye in cosmic terms. Yet amid this destruction, there's a strange irony. The same radiation that's erasing these disks also lights them up, making them visible to us in stunning detail. Without it, we might never have spotted them at all, but not all Proplyds are doomed. Some lie in shadowed pockets, shielded by dense curtains of gas, where the chaos outside actually helps. Radiation pressure can compress the disks, triggering faster clumping of particles, like a cosmic snowplow piling up material where planets might one day form. Others are far enough from the trapezium stars that their evaporation is slow, giving them millions of years to build worlds in peace. These resilient disks could be the ones that mature into something familiar, stable solar systems with rocky planets, gas giants, and maybe, just maybe, the right conditions for life. What's truly mind-bending is that we're seeing Proplyds at every stage of their lives, from pristine disks still cloaked in dust to those on the verge of disintegration. It's like walking through a nursery where some cribs are being gently rocked while others are caught in a hurricane. Each one tells a story about how solar systems form, how they die, and how incredibly lucky we are that our own sun didn't grow up in a neighborhood this violent. The Orion Nebula's Proplyds are a reminder the universe isn't just vast, it's ruthless, beautiful, and above all, unpredictable. Deep in the tangled heart of the Orion Nebula, where dust clouds blot out starlight and temperatures plunge to near absolute zero, something monstrous hides. The Becklin-Neugebauer object, or BN object for short, isn't just another star. It's a cosmic phantom, a celestial heavyweight lurking behind curtains of dust so thick visible light can't escape. For centuries, telescopes staring at this patch of sky saw nothing but darkness. Then came infrared astronomy, peeling back those layers like an X-ray revealing secrets beneath skin. What scientists found rewrote the rules for how massive stars can form in plain sight while remaining utterly invisible. This isn't just some dim, aging star fading into obscurity. The BN object is a behemoth, a young, massive star packing 30 times the sun's heft into a body only a few 100,000 years old. Its cradle of dust isn't a shroud of death, but a birth blanket so dense, even the star's furious radiation can't blast through. Yet infrared eyes see the truth. This hidden titan glows white-hot, its light absorbed and re-emitted by the surrounding dust as eerie thermal whispers. That's how astronomers first spotted it, not by the star itself, but by the ghostly halo of warmth radiating from its prison. What makes this object so baffling isn't just its stealth. It's moving fast. Observations show the BN object rocketing through its dusty cocoon at 60,000 miles per hour, leaving a wake of shocked gas in its path. Some theories suggest it was violently ejected from the Trapezium Cluster's gravitational brawl, flung outward like a cosmic slingshot. Others propose it's locked in a deadly dance with another hidden star, their mutual orbits spiraling toward catastrophe. Whatever the cause, its motion defies the serene image of stellar nurseries we once imagined. But the real mystery, this star shouldn't exist, at least not where it is. Massive stars typically form deep within nebulae's coldest, densest cores. Yet the BN object sits oddly exposed, wrapped in just enough dust to hide it, but not enough to explain its birth. Some researchers speculate it's a runaway, born elsewhere and now drifting through foreign gas. Others think we're witnessing a rare snapshot, a fleeting moment when a star's birth cocoon hasn't yet fully dispersed, giving us a chance to study what most massive stars hide, their messy, violent infancies. And then there's the infrared echo. Recent studies reveal the BN object isn't alone. Its light, delayed by centuries of travel through dust, creates eerie, light echoes, ghostly rings expanding outward like ripples from a stone tossed into a pond. These echoes aren't just pretty, they're time machines showing us how the star's brightness changed hundreds of years ago. Together, they paint a portrait of a star that's anything but stable, flaring unpredictably as it devours its surroundings. The Nebula object forces us to confront a humbling truth. Even in our cosmic backyard, the universe keeps secrets. It's a reminder that for all our telescopes and technology, some of the most dramatic players in the cosmos prefer to lurk in the shadows, revealing themselves only when we learn to look in ways we never imagined. And out there, in the Orion Nebula's swirling depths, who knows how many more phantoms like it wait to be found? The Orion Nebula isn't just a birthplace for stars, it's also a graveyard. Buried within its glowing gas lies the aftermath of one of the most violent cosmic events ever witnessed, the BNKL explosion. This wasn't some slow-motion stellar evolution. It was a detonation so powerful, it sent shockwaves rippling through the nebula at speeds topping 200,000 miles per hour, leaving behind a debris field that still glows centuries later. Imagine a bomb blast frozen in time, its echo reverberating through space. Only this bomb was a collision or eruption involving stars, and its remnants tell a story we're still piecing together. The first clues came from infrared telescopes, which revealed a bizarre, clumpy structure near the Nebula object. Instead of the smooth gas clouds typical of the nebula, this region, dubbed the BNKL area, was littered with jagged filaments and knots of superheated gas, all racing outward in a pattern that screamed explosion. Millimeter wave observations added to the mystery, detecting vast plumes of silicon monoxide, a tracer of violent shocks streaking through the chaos like cosmic shrapnel. The energy involved was staggering, equivalent to 10,000 suns shining at once, unleashed in what may have been just a few earth-shaking moments. So what caused it? The leading theory is a stellar collision, two young, massive stars spiraling into each other in a gravitational death spiral. In the crowded core of the nebula, where stars are packed tighter than rush-hour commuters, such crashes might be more common than we thought. Simulations suggest that if two stars several times heavier than our Sun locked into a close orbit, their dance could end catastrophically, merging into a single, unstable behemoth that detonates like a celestial grenade. The resulting fireball would explain the expanding debris, the scorched gas, even the bizarre distribution of heavy elements now littering the site. But there's a twist. Some researchers argue the explosion wasn't a collision at all, but a failed supernova. In this scenario, a single massive star, perhaps 100 times the Sun's mass, grew unstable and underwent a partial collapse. Instead of exploding completely, it might have ejected its outer layers in a titanic belch, leaving behind a dense remnant that either became a black hole or vanished entirely. The shockwaves from such an event would match the messy aftermath we see today, including the way certain molecules like water and carbon monoxide were hurled outward at different speeds. Then there's the wild card, magnetic monstrosity. Recent studies hint that the BNKL region is threaded with enormously powerful magnetic fields, trillions of times stronger than Earth's. Could these fields have stored up energy like a coiled spring, only to snap and unleash it in a single, devastating rupture? It's a fringe idea, but if true, it would rewrite our understanding of how nebulae channel energy, turning the Orion Nebula into a cosmic capacitor, capable of storing and releasing violence on an unimaginable scale. The most haunting detail, this explosion wasn't ancient history. Based on the expansion rate of the debris, astronomers estimate it happened just a few hundred years ago, around the time Galileo first pointed his telescope skyward. Had it occurred in a more visible part of the sky, the blast might have outshone the moon for weeks, a spectacle visible even in daylight. Instead, hidden behind veils of dust, it remained invisible until modern technology peeled back the layers. Now, centuries later, we're left with forensic evidence scattered across light years, a crime scene where the universe reminds us, even its most beautiful nurseries have teeth. The BNKL explosion isn't just a relic, it's a warning. A glimpse into the chaotic, destructive processes that shape the cosmos as surely as gravity and starlight. And somewhere in that wreckage, amid the glowing tendrils and fleeing gas, lies the answer to a question we're only beginning to ask. In the Orion Nebula's crowded stellar metropolis, how often do these catastrophes occur? And could one happen again, tonight, hidden behind the Orion Nebula's shimmering curtain of light? A darker, denser monster lurks, the Orion Molecular Cloud 1, or OMC1 for short. This isn't just another pocket of gas, it's a star factory operating at maximum capacity, a place so thick with cosmic raw material that sunlight can't penetrate it. If the visible nebula is the glittering showroom, OMC1 is the messy workshop in the back where stars aren't just born, they're forged in chaos. What makes this cloud so special? Scale, stretching dozens of light years across and weighing in at over 100,000 times the mass of our Sun, it's a reservoir of cold hydrogen, helium, and dust so vast it could spawn thousands of new stars. But it's not the size alone that baffles astronomers, it's the way this cloud moves. Recent radio telescope observations reveal OMC1 isn't sitting still. It's a churning, writhing beast with filaments of gas twisting like electrified snakes and entire regions collapsing under their own gravity. Some streams flow inward, feeding newborn stars, while others whip outward at terrifying speeds, ejected by violent stellar bursts. The most striking features are the filaments, thread-like structures so long and thin, they defy logic. Some stretch for light years yet are only a few times wider than our solar system, like cosmic spider silk. Scientists believe these filaments are the universe's scaffolding, the secret blueprint for how star clusters assemble. Gravity pulls gas into these narrow strands, which then fragment into dense knots where stars ignite. It's a process so efficient, OMC1 has become one of the most prolific star-forming regions we've ever observed. But here's the twist, not all filaments are created equal. Some glow faintly with the heat of newborn stars, while others remain eerily dark, their interiors so shielded from radiation they're among the coldest places in the universe, just a few degrees above absolute zero. These icy veins might hold clues to one of astronomy's biggest mysteries, how complex molecules, the precursors to life, form in the void. Already, telescopes have detected compounds like methanol, formaldehyde, and even glycine, an amino acid clinging to dust grains in these frozen rivers. The real fireworks start when these filaments snap. In one infamous region near OMC1's core, astronomers witnessed a gravitational pileup, 4 massive protostars crashing into each other's orbits, their mutual pull shredding the surrounding gas into chaotic streamers. The energy released was staggering, launching shockwaves that distorted magnetic fields and sent tower-like pillars of dust rippling outward. This single event might have birthed an entire cluster of stars, all from one catastrophic collapse. Yet for all its violence, OMC1 has a rhythm. Submillimeter telescopes pick up faint vibrations rippling through the cloud sound waves so deep, they'd register as musical notes 57 octaves below middle C if humans could hear them. These are the cloud's heartbeat, the reverberations of star formation itself, and they're proof that even in this maelstrom there's order. The universe doesn't build stars at random. It follows patterns, ones we're only beginning to decode. What's unfolding inside OMC1 isn't just a spectacle, it's a time capsule. The processes here mirror those that birthed our own sun and planets 4.6 billion years ago. Every twisted filament, every collapsing knot is a window into how solar systems, and perhaps life, might arise elsewhere in the cosmos. The Orion molecular cloud one doesn't just make stars. It holds the recipe for worlds, and somewhere in its depths right now, another sun might be flickering to life, wrapped in dust, waiting for its turn to shine. Stretching across the Orion Nebula like jagged cracks in a stained glass window, the dark lanes are more than just empty space, they're towering walls of cosmic soot, dense enough to swallow starlight whole. These Inkai filaments, some wider than our solar system, aren't shadows cast by distant objects. They're mountains of cold carbon-rich dust and molecular gas, frozen so solid that even the nebula's fierce ultraviolet radiation can't penetrate them. Imagine smoke from a billion extinguished campfires, frozen into tendrils so thick they blot out entire star clusters behind them. Hubble's images capture their eerie beauty, jet black rivers cutting through neon gas, their edges so sharply defined they look painted onto the cosmos. But these lanes aren't passive curtains, they're dynamic structures sculpted by forces we're only beginning to understand. At their cores, temperatures plunge to just 10 degrees above absolute zero, cold enough to freeze hydrogen solid. Here, molecules huddle together in the dark, forming exotic ices coating every dust grain like cosmic frost. Radio telescopes have detected bizarre chemicals in these frozen vault cyanopolyines, chain-like molecules rarely seen elsewhere in space, and even tentative signs of benzene rings, the building blocks of more complex organics. It's as if the universe is running chemistry experiments in these lightless pockets, brewing compounds too fragile to survive the nebula's radiation-filled arenas. The real magic happens at the edges where the dark lanes meet the nebula's glow. Ultraviolet light from the trapezium stars slams into these dust walls, creating glowing ionization fronts, thin, luminous skins where atoms are ripped apart and reassembled in real time. In some places, the radiation erodes the lanes like a sandblaster, carving out surreal pillars that resemble twisted chimneys. Elsewhere, the dust pushes back, its sheer density protecting pockets of gas long enough for gravity to collapse them into new stars. This tug-of-war between destruction and creation gives the lanes their strange, wispy shapes, as if some cosmic hand is dragging fingers through wet paint. What truly baffles astronomers is how these structures remain intact at all. Given the nebula's turbulent environment, they should have dissipated millennia ago. Yet some lanes persist for light years, their structures suspiciously coherent. The leading theory, magnetic fields, invisible lines of force stronger than steel, might be threading through the dust like rebar in concrete, holding the lanes together against the chaos. Recent polarimetry measurements support this, showing dust grains aligned along field lines like compass needles, a telltale sign of magnetic influence. If confirmed, it would mean these dark veins aren't just debris, they're cosmic infrastructure shaped by forces far subtler than gravity alone. Then there are the shadows. When foreground lanes pass in front of glowing gas clouds, they cast silhouettes so detailed, astronomers can map their structures like celestial X-rays. One famous example, the Dark Sword, is a lane so perfectly aligned that it projects a shadow stretching 15 trillion miles, with tiny knots in the dust visible as bumps along its edge. These aren't static images. Time-lapse observations reveal some shadows shifting over decades, proof that the lanes are slowly churning, their dust grains clumping and dispersing in slow motion. Most haunting are the hidden nurseries. Infrared telescopes peer straight through these dark lanes, revealing baby stars buried deep within them, stellar embryos wrapped in dust so thick, not a single photon of visible light escapes. Some of these protostars are ejecting jets that punch holes in their dusty cocoons, creating glowing tunnels that curve like corkscrews. Others sit motionless, their growth stunted by the very material that birthed them, as if the lanes giveth and taketh away. The Orion Nebula's dark lanes are more than gaps in the light. They're laboratories of extremes where chemistry operates in slow motion, where magnetic fields trump gravity, and where new stars are born in darkness so complete their first cries are infrared whispers. To study them is to glimpse the universe's hidden half, the shadowy counterpart to all that glitters, and perhaps in their icy depths they hold clues to how life's ingredients survive and thrive in the most unforgiving corners of space. Among the Orion Nebula's many violent spectacles, few are as mesmerizing or as downright bizarre as the supersonic fire hose known as the HH-34 jet. Stretching over 1.5 light-years through space, this luminous whip of plasma isn't just a static cosmic feature. It's a living, writhing structure, twisting and knotting itself in real time, a time-lapse of stellar fury unfolding before our eyes. At its source, a newborn star no more than a few 100,000 years old spews out twin beams of superheated gas at 500,000 miles per hour, each particle screaming through the void fast enough to cross the United States in under 5 seconds. What makes HH-34 stand out isn't just its speed. It's the way it moves. Hubble's time-lapse observations, spanning 2 decades, reveal a jet that behaves less like a steady stream and more like a flailing garden hose. The plasma doesn't flow smoothly. It erupts in sporadic bursts, creating glowing beads of gas that surge forward before suddenly slowing, stacking up like traffic on a cosmic freeway. These knots, each larger than our solar system, shimmer with eerie green-blue hues as shockwaves ripple through them, heating the gas until it fluoresces. The result, a chain of cosmic pearls strung across the abyss, but the real mystery lies in the jet structure. Instead of shooting straight, HH-34 corkscrews wildly, its path warped into a helical spiral. Some astronomers believe an unseen companion star might be tugging on the newborn stellar engine, its gravity wobbling the jet like a top. Others suspect powerful magnetic fields, twisted into coils by the star's rapid rotation, act as invisible rails guiding the outflow. The effect is both mesmerizing and alien, a celestial tornado spinning itself into existence, one violent knot at a time. Here's where it gets stranger. The jet isn't alone. Opposite it, an identical but fainter beam fires in the exact opposite direction, a mirror image of destruction. Together, they form what's known as a bipolar outflow, a hallmark of stellar infancy. As the young star devours gas from its surrounding disk, it also ejects a fraction of that material in these polar jets, a cosmic balancing act that prevents it from spinning itself apart. The energy involved is staggering. Each second, the star expels more mass than flows over Niagara Falls in a year. Yet amid this chaos, there's precision. The jet interacts with the nebula's surrounding gas like a sculptor chiseling marble, carving out cavities and triggering secondary shockwaves that glow for light years downstream. Some of these shock fronts travel so fast they've outpaced the jet itself, creating bow-shaped ripples resembling sonic booms frozen in space, and the knots. They're not just pretty, they're cosmic speedometers. By tracking their motion over years, astronomers have calculated the jet's velocity, its flickering brightness, even the spin rate of the star that powers it. The most haunting detail, HH34 won't last forever. In a few thousand years, a blink in cosmic time, the jet will dissipate, its energy absorbed by the nebula. The star, now matured, will cease its tantrum, leaving only faded shockwaves as evidence of its violent youth. But for now, it's a front-row seat to one of the universe's most dramatic processes, a star's birth cries written in plasma across the sky. And every twist, every knot is a sentence in that story, one we're only just learning to read. At first glance, the Orion Nebula seems like an open book, a radiant cloud of gas and young stars where everything is on display. But peer deeper and an unsettling gap emerges in our understanding. This cosmic nursery is missing something fundamental, nearly 80% of its expected mass. That's right, for all its luminous beauty, the nebula's visible material accounts for only a fraction of what gravity says should be there. It's like weighing a suitcase and finding it light, even though you packed it to the brim. This isn't just a rounding error, it's a glaring cosmic discrepancy that has astronomers chasing shadows. So where is the missing mass? One leading theory points to the nebula's dark, dusty corners, regions so dense they hide entire stellar nurseries from view. Infrared telescopes have already exposed some of these secrets, revealing protostars and brown dwarfs too dim to glow in visible light. But even adding these faint objects to the ledger leaves the balance sheet woefully short. Could there be an entire population of failed stars, objects barely larger than Jupiter lurking undetected? Or perhaps rogue planets untethered from any sun, drifting like ghosts through the nebula's depths? Then there's the black hole hypothesis. Some researchers speculate that intermediate mass black holes, objects heftier than typical stellar remnants but smaller than galactic giants, might be hiding in the chaos. These stealthy predators wouldn't emit light unless actively feeding, making them nearly invisible against the nebula's glow. Yet their gravity would leave fingerprints, subtly warping the motions of nearby stars and gas. So far, searches for such distortions have come up empty, but the possibility remains tantalizing. The wild card, dark matter. Ordinarily, we associate this mysterious substance with vast galactic halos, not stellar nurseries. But what if filaments of dark matter weave through the nebula, their gravitational pull anchoring gas clouds together? It's a radical idea, but not impossible. Simulations show that even trace amounts could explain the nebula's peculiar kinematics, how some gas streams move faster than gravity alone should allow. Here's the twist: the missing mass might not be missing at all. Alternative theories suggest we're misreading the nebula's structure entirely. Turbulence and magnetic fields could be propping up gas clouds, reducing the need for extra mass to hold them together. Or perhaps past supernovae have already blown much of the material away, leaving behind a hollowed-out shell that only appears intact. The stakes are higher than they seem. Solve this puzzle, and we might unlock secrets about how star clusters form, and why some, like our own solar system's birthplace, disperse while others endure. Every photon we collect, every spectrum we analyze, brings us closer to an answer. Until then, the Orion Nebula keeps its secrets, reminding us that even the brightest corners of the cosmos hold shadows we've yet to illuminate. At the heart of the Orion Nebula's chaos, one star doesn't just shine, it commands. To one Orionis C isn't just the brightest member of the Trapezium Cluster, it's a cosmic powerhouse with a magnetic personality, literally. This blue giant, 30 times more massive than our Sun, generates a magnetic field so intense it defies everything we know about stellar physics. Clocking in at over 1,000 times stronger than Earth's protective magnetosphere, this invisible force grips the surrounding nebula like an iron hand, bending ionized gas into surreal shapes and sparking phenomena unseen anywhere else in the cosmos. What makes this star's magnetism so baffling? Massive stars like Theta-1c aren't supposed to have strong magnetic fields, at least not according to classic models. These behemoths churn so violently, their internal dynamos should scramble magnetic lines like eggs in a blender. Yet here, the field isn't just stable, it's structured, with clear north and south poles like a colossal bar magnet floating in space. Some astronomers suspect a violent past, perhaps a collision with another star, could have imprinted this magnetic signature, like a cosmic scar frozen in time. Others propose exotic physics, where the star's rapid rotation and seething plasma layers amplify the field beyond theoretical limits. The real spectacle lies in how this magnetism shapes the nebula. Ultraviolet radiation from Theta-1c already shreds nearby gas clouds, but add its magnetic whip to the mix, and things get truly strange. Charged particles, instead of streaming away evenly, spiral along magnetic field lines like beads on a wire, creating glowing braids of plasma that stretch for light years. Hubble images reveal these structures in eerie detail, luminous tendrils curling like fiddlehead ferns, their shapes dictated by the star's invisible influence. In some regions, the field acts like a cosmic press, compressing gas into dense sheets that glow brighter than the surrounding nebula. Elsewhere, it funnels stellar winds into narrow jets, accelerating particles to near light speeds. Then there's the magnetic bubble. Measurements show Theta-1c's field extends over 4 light-years, carving out a teardrop-shaped cavity in the nebula. Gas can't cross these invisible walls easily. Instead, it piles up at the edges, forming shock fronts that ripple like waves against a pier. This isn't just stellar weather, it's a fundamental reshaping of the nebula's architecture. The bubble even deflects radiation, creating shadowed zones where molecules can form in peace. Some researchers believe these protected pockets might be crucial nurseries for complex organic chemistry, shielded long enough for prebiotic compounds to take root. The most dramatic evidence of this star's influence, the Big Arc. Radio telescopes have detected a vast crescent-shaped structure near Theta-1c, made of energized electrons whipping around magnetic lines. Stretching twice the width of our solar system, this feature glows faintly in radio waves, a ghostly halo suspended in the nebula's glow. Its very existence suggests the star's magnetism isn't just strong, it's dynamic, capable of rearranging entire sectors of space on scales we're only beginning to map. Theta-1 Orionis C forces us to rethink the role of magnetism in cosmic evolution. Before its discovery, we assumed massive stars shaped their surroundings through radiation and winds alone. Now we know their invisible magnetic fingerprints might be just as important, sculpting gas, guiding stellar births, even shielding the ingredients for life. As this stellar monarch reigns over the Orion Nebula, its influence whispers a tantalizing possibility. Magnetism might be the universe's silent architect, weaving order into chaos, one invisible thread at a time. Amid the Orion Nebula's tapestry of pinks and blues, one color dominates with an otherworldly intensity, a luminous green so vivid it looks almost artificial. This isn't the gentle verdant glow of auroras or the emerald shimmer of distant galaxies. It's a searing, electric hue radiating from the nebula's heart, a signature so distinctive, astronomers once dubbed it celestial neon. But the source of this eerie light isn't some exotic element or alien chemistry. It's oxygen, the same life-giving gas we breathe, behaving in ways that defy ordinary physics. When ultraviolet radiation from the Trapezium Cluster's massive stars slams into the nebula's gas clouds, it doesn't just heat them, it tears atoms apart. Oxygen atoms, stripped of electrons, become ionized, their remaining electrons jumping to higher energy levels like overcharged springs. As these electrons settle back down, they release energy in the form of light, specifically at wavelengths our eyes perceive as green. This process, called doubly ionized oxygen emission, creates the nebula's signature glow, But here's the catch: this particular shade of green is vanishingly rare in the cosmos. Most nebulae lean toward reds from hydrogen or blues from scattered starlight, making the Orion Nebula's emerald blaze an outlier. Why is this oxygen glow so unusual? It demands perfect cosmic conditions. The star's radiation must be strong enough to strip oxygen atoms of 2 electrons, a feat only the hottest, most massive stars can achieve. Then the surrounding gas can't be too dense, otherwise collisions between atoms would bleed away the energy before it can glow. It's like trying to sustain a fireworks spark in a hurricane. The Orion Nebula hits this sweet spot. Its proximity to Earth, just 1,300 light-years away, and its perfect balance of radiation and thin gas make it one of the best laboratories to study this phenomenon. Yet the green glow hides a cosmic irony. That vibrant hue we see, it's technically a forbidden transition. In the vacuum of space, the rules of quantum physics say these oxygen emissions should happen so rarely, they're practically impossible. On Earth, in labs, oxygen would never glow like this. Our atmosphere's density would quench the effect instantly. But in the nebula's near-perfect vacuum, atoms linger in excited states long enough for the forbidden to become commonplace. It's a reminder that the universe operates on a different rulebook when freed from earthly constraints. Compare this to other nebulae and the difference is stark. The Crab Nebula's filamentary tendrils glow blue-white from synchrotron radiation, charged particles spiraling in magnetic fields. The Carina Nebula blushes pink with hydrogen alpha emissions. But Orion's green, it's a fingerprint of violence, a direct result of the Trapezium star's relentless ultraviolet assault. The hue isn't uniform either. Near the cluster, it's almost fluorescent, fading to a softer teal at the edges where radiation weakens. In some regions, magnetic fields twist the glowing oxygen into ribbons, creating psychedelic swirls visible only through narrowband filters. The most fascinating detail: this green glow isn't eternal. As the nebula evolves, the trapezium stars will either explode as supernova or drift apart, their radiation fading. The oxygen emissions will dim, leaving future observers, human or otherwise, with a very different Orion Nebula. For now, though, that radiant green stands as a lighthouse in the cosmos, a beacon of celestial chemistry so precise, so fragile, it's a wonder we get to witness it at all. Towering like frozen tidal waves caught mid-crash, the Orion Nebula's fingers of gas stretch defiantly against the stellar onslaught surrounding them. These dark, pillar-like structures, some twice the height of our solar system, aren't just cosmic scenery. They're the last survivors of a gas cloud being slowly erased by the very stars it birthed. You might recognize their cousins, the famous pillars of creation in the Eagle Nebula, but make no mistake, Orion's fingers have their own eerie story to tell. Where the Eagle's pillars stand in relative isolation, these formations exist in a war zone, bombarded from all sides by ultraviolet fury and supersonic winds. The sculpting begins with the Trapezium Cluster's most massive stars, whose radiation acts like a celestial sandblaster. Imagine a candle held too close to a block of ice. The surface melts unevenly, leaving peaks and valleys. That's precisely what's happening here, but on an interstellar scale. The fingers aren't solid objects, they're denser patches of molecular gas that resisted evaporation longer than their surroundings. Their knotted heads, seen in infrared, actually cradle fledgling stars deep within, their gravity anchoring the gas against the storm. Meanwhile, the wrinkles along their lengths, those jagged ridges and filamentary tendrils, are shockwaves frozen in time, evidence of past explosions and stellar winds crashing against them like waves on a cliffside. Hubble's portraits reveal the violence in exquisite detail. The fingers' tops glow electric blue where radiation excites the gas, while their shadowy bases remain eerily dark, shielded from the assault. But the most breathtaking features are the tiny protuberances nicknamed evaporating gaseous globules or egg that dot their surfaces like blisters. These are stellar wombs, pockets of gas so dense they're collapsing into new stars even as the pillars themselves disintegrate. It's a race against time. Will the stars inside mature before their cocoons are stripped away? Some will win, bursting free to join the nebula's glittering tapestry. Others will be aborted mid-formation, their material scattered back into the void. What makes these structures truly surreal is their motion. Time-lapse observations show the fingers aren't static, they're fleeing. Stellar winds push them at speeds topping 100,000 miles per hour, elongating their shapes and shearing off fragments that glow briefly before vanishing. Astronomers estimate they have maybe 10,000 years left, a heartbeat in cosmic terms, before they're completely erased. Yet even in their destruction, they're creators. The same winds tearing them apart compress gas along their lengths, triggering new rounds of star formation in their wakes. It's a paradox written across light years. The fingers are both dying and giving birth simultaneously, their silhouettes a fleeting signature of the nebula's endless cycle of creation and destruction. Standing as monuments to impermanence, these ephemeral giants remind us that even the most colossal structures in the universe are at the mercy of time and tide. They're not just fingers, they're hourglasses, counting down the moments until they dissolve into starlight, leaving behind only the celestial children they sheltered in their shadow. Scattered across the Orion Nebula like cosmic soap bubbles, these delicate spherical cavities might look like serene pockets of calm, but don't be fooled. Each one is a battlefield, a fleeting monument to the brutal winds screaming from newborn stars. These bubbles form when a massive young star, still devouring gas from its surroundings, blasts out a hurricane of charged particles at nearly 1,000,000 miles per hour. The force is unimaginable enough to carve out voids in the surrounding gas big enough to swallow our solar system whole. And just like soap bubbles, they're astonishingly fragile, destined to pop within a cosmic blink as the nebula's chaos engulfs them. What's mesmerizing isn't just their size. Some stretch 2 light years across, but their perfect geometry. In a nebula where everything else twists and churns, these bubbles remain eerily round, their edges glowing as shock-heated gas rams into cooler material. Hubble's sharp eyes reveal intricate textures along their surfaces, ripples from smaller stellar winds, tiny jets punching through like needles, even secondary bubbles budding off like celestial froth. Each detail tells a story of pressure and resistance, a tug of war between creation and destruction. But here's the real twist: these bubbles aren't empty. Peer inside with infrared telescopes and you'll find them bustling with activity. Some cradle fledgling stars in their walls, their growth stunted by the very winds that carved their refuge. Others trap pockets of superheated gas, glowing like embers in a dying fire. The most bizarre are bubble chains, where multiple stars have blown sequential cavities, creating a string of orbs that resemble a cosmic bubble wand dipped in starlight. Their fleeting existence makes them cosmic gold mines. Unlike the nebula's larger structures, which evolve over millennia, these bubbles change visibly within human lifetimes. Astronomers have watched some expand by billions of miles in just decades, while others collapse abruptly when a neighboring star's wind shifts direction. It's a reminder that even in the vastness of space, some of the most dramatic events unfold on timescales we can almost grasp, and when they finally burst, their gas doesn't vanish, it rejoins the nebula's churning currents, ready to be recycled into the next generation of stars, planets, or perhaps one day, something even more extraordinary. Among the Orion Nebula's swirling chaos, not all stars stick around to bask in the glow of their birthplace. Some are flung into the void like cosmic outcast stellar runaways racing through space at speeds that defy gravity's grip. These aren't leisurely wanderers, they're bullets fired from the nebula's heart, hurtling outward at hundreds of thousands of miles per hour, their trajectories marked by glowing shockwaves that stretch like scars across the gas clouds. What could possibly launch a star with such violence? The answer lies in the ultimate celestial game of tug of war. Take the case of the Nebula object, that massive, dust-shrouded star we met earlier. Its breakneck motion suggests it was once part of the Trapezium Cluster's gravitational mosh pit until a close encounter with another heavyweight star sent it careening into exile. In stellar terms, it's the equivalent of being thrown from a moving car, but the BN object isn't alone. Infrared surveys have uncovered dozens of these fugitives, some solo, others in pairs, all fleeing the nebula with their stellar tails tucked between their legs. Their escape routes aren't random. They trace backward to the nebula's core like breadcrumbs leading to the scene of the crime. The mechanics behind these ejections are both elegant and brutal. When two or more massive stars engage in a gravitational dance, their orbits can grow unstable, especially in crowded nurseries like the Trapezium. A passing third star might disrupt the balance, sending one participant spiraling inward while the other gets slingshot outward at astonishing speeds. The math is chillingly precise. For every star that plunges deeper into the cluster, another gains enough kinetic energy to break free entirely. It's nature's way of restoring order, sacrificing a few to stabilize the many. But the real drama unfolds in their wakes. As these runaways plow through the nebula's delicate gas, they create bow shocks, luminous arcs of compressed material glowing like cosmic headlights. Hubble has captured these structures in exquisite detail, some shaped like crescent moons, others twisted into spirals by the star's rotation. The most extreme examples sport tales of ionized gas stretching light years behind them, evidence of their unrelenting speed. One particularly furious runaway, dubbed Source X, has left a trail so massive it could span the distance from Earth to Alpha Centauri twice over. Where does this road lead? For some, it's a lonely journey into interstellar space, where they'll drift until the Milky Way's tides pull them into some distant star cluster. Others might skim the nebula's outer edges, their gravity stirring up fresh waves of star formation as they pass. The unluckiest could collide with dense gas clouds, triggering new rounds of chaos. But here's the twist: these runaways aren't just casualties. They're delivery systems. As they flee, they carry heavy elements forged in the nebula's core, scattering them across the galaxy like cosmic Johnny Appleseeds. Perhaps the most poetic fate belongs to the binary runaways, pairs of stars still gravitationally bound even as they race through the void. Their dance continues, but now against the backdrop of infinite space, a private waltz with no audience but the cosmos itself. For astronomers, these pairs are gold mines, their motions revealing secrets about the nebula's gravitational history that static stars could never tell. The Orion Nebula's runaway stars remind us that creation isn't always gentle. Sometimes it's a messy, violent affair where even the mighty can become exiles. Yet in their exile, they transform from local phenomena to galactic voyagers, carrying pieces of their birthplace farther than any nebula-bound star ever could. They're proof that even in the universe's most crowded neighborhoods, there's always an exit, and sometimes it's one way. Amid the Orion Nebula's shimmering glow, some of the most intriguing structures aren't bright at all, they're shadows. These so-called silhouette disks appear as inky black smudges against the nebula's radiant backdrop, not because they're empty, but because they're so densely packed with gas and dust they swallow starlight whole. Picture a child's hand held up to a projector. The fingers block the light, casting a dark outline on the wall. That's exactly what's happening here, but on a cosmic scale, with these disks stretching wider than our entire solar system. What makes these shadows so special? They're not just cosmic clutter, they're protoplanetary disks caught in the act of forming planets. While most disks in the nebula glow faintly as they're heated by nearby stars, silhouette disks are oriented edge-on from our perspective, their thick rims shielding their inner material from radiation. This alignment gives astronomers a rare opportunity to study the raw ingredients of planet formation without the glare of starlight interfering. Hubble's sharp vision reveals intricate details, jagged edges where dust clumps are beginning to coalesce, and asymmetrical shapes hinting at gravitational tug-of-wars between budding worlds. Detecting these disks requires more than just keen eyes. It's a feat of cosmic detective work. Since they don't emit their own light, scientists rely on the absence of it, mapping the nebula's background glow to pinpoint where starlight abruptly vanishes. Advanced instruments like the Atacama Large Millimeter Array then peer through the darkness at longer wavelengths, revealing the disk's cold, dusty structures in stunning detail. Some even show telltale gaps, clean lanes carved by newborn planets sweeping up debris like snowplows clearing a path. The most fascinating silhouette disks defy expectations. A few exhibit bizarre spiral arms twisted like coiled springs, a sign of gravitational instabilities that could accelerate planet formation. Others flicker unpredictably, their shadows deepening or fading as clumps of dust pass in front of background stars. One particularly eerie specimen, nicknamed the Dark Wheel, even shows spokes of denser material radiating from its center, as if some unseen force is sculpting it from within. These shadowy disks aren't just curiosities, they're time capsules. Locked within their frozen particles could be the very same materials that once swirled around our own infant sun before Earth or any other planet took shape. And because the Orion Nebula is so close, we're witnessing this process unfold in what's essentially real time, a front-row seat to the birth of solar systems that might one day harbor worlds not so different from our own. The Orion Nebula dazzles in visible light, but swap the lens to infrared, and an entirely different universe emerges, one where hidden giants stir beneath veils of dust, where cold clouds glow with unexpected warmth, and where the nebula's true scale reveals itself in ways the human eye could never perceive. Infrared astronomy peels back the nebula's radiant facade like an X-ray, exposing secrets buried for millennia. Take the Becklen-Neugebauer object, that massive runaway star we met earlier. To optical telescopes, it's just a shadow, but in infrared, it blazes like a lighthouse, its heat signature cutting through the dust that shrouds it. And it's not alone. Entire stellar nurseries, invisible in Hubble's iconic images, suddenly flicker to life when viewed in thermal light, proving that what we see with our eyes is just a fraction of the story. The James Webb Space Telescope has revolutionized this hidden landscape. With its unprecedented infrared sensitivity, JWST has spotted protostars so young, they're still swaddled in blankets of gas so thick, not a single photon of visible light escapes. Some of these infant stars are caught in the act of firing off jets, narrow beams of particles that glow brilliantly in infrared as they slam into surrounding material. Others are ringed by vast, warped disks of warm dust, the raw material for future planetary systems. But the real shockers are the failed stars, brown dwarfs too small to ignite hydrogen fusion, yet large enough to glow dimly in infrared. These cosmic in-betweeners, some no hotter than a campfire, challenge our definitions of what a star even is. Then there's the dust itself. In visible light, the nebula's dark lanes appear empty. Infrared reveals them as intricate networks of warm filaments, some threaded with complex organic molecules like formaldehyde and methanol. These aren't just passive clouds, they're dynamic structures, vibrating with subtle motions that suggest magnetic fields are braiding them like rope. JWST has even detected hotspots within these frigid dust lanes, pockets where unknown processes are heating grains to hundreds of degrees, creating tiny oases in an otherwise frozen desert. Perhaps the most haunting infrared discovery is the nebula's ghost stars, objects so deeply embedded in dust, their light takes centuries to escape. When we observe them, we're seeing photons emitted when Shakespeare penned his plays, their journey delayed by the nebula's opaque walls. These time-lagged signals act like cosmic echoes, allowing astronomers to reconstruct how the nebula's brightest stars have changed over generations. The lesson is clear. The Orion Nebula's true majesty lies beyond the visible spectrum. What looks like a well-mapped neighborhood in optical light becomes an uncharted frontier in infrared, full of surprises that rewrite our understanding of stellar birth. And with JWST eyes now wide open, who knows what other ghosts or giants might still be lurking in the shadows? Beneath the Orion Nebula's dazzling visible light display lies a hidden layer of chaos, one that only X-ray vision can reveal. While Hubble serves us postcard-perfect hues of pink and green, telescopes like Chandra expose a far more violent reality. A seething underworld of million-degree plasma, freakish stellar tantrums, and cosmic mysteries that defy explanation. This isn't the nebula you thought you knew. It's a high-energy battleground where newborn stars wage war on their own surroundings and where shadows flicker with forces we've yet to understand. Take the Trapezium Cluster's young stars, those same suns that paint the nebula with ultraviolet brushstrokes. In X-rays, they transform into unruly monsters, launching flares so powerful they outshine our own sun by 100,000 times in mere seconds. These aren't ordinary solar flares. They're cataclysmic eruptions, magnetic reconnections on a scale that twists entire stellar atmospheres like rubber bands until they snap. Some flares last minutes, others rage for days, their X-ray signatures looping and spiking like a frenzied heart monitor. The energy released could strip atmospheres off nearby planets before they've even finished forming, a stark reminder that stellar infancy isn't just about birth but survival. Then there are the X-ray ghosts, diffuse, looping structures with no obvious source. These vast, faint rings of high-energy emission hover like cosmic jellyfish, some stretching multiple light-years across. One leading theory suggests they're shockwaves from long-dead supernova, their remnants glowing faintly in X-rays as they collide with the nebula's gas. Others propose they're magnetic bubbles inflated by stellar winds and lit up when charged particles spiral along invisible field lines, the eeriest part. A few seem to pulse, their brightness waxing and waning over decades, as if something unseen is breathing life into them. But the real enigma is the X-ray background, a faint, omnipresent glow that permeates the nebula even where no stars are visible. At first, astronomers assumed it was just scattered emission from known sources. Then Chandra's razor-sharp resolution revealed the truth. Hundreds of previously invisible objects, each a pinpoint of X-ray light. Some are likely brown dwarfs, failed stars too cool to shine visibly but still capable of violent magnetic outbursts. Others could be neutron stars or black holes, hidden in plain sight, their high-energy signatures betraying their presence. And a handful, their origins remain utterly unknown, flaring unpredictably before vanishing back into the noise. One particularly bizarre X-ray source, dubbed Orion's Spark, behaves like nothing else in the nebula. It erupts every few days with clockwork regularity, blasting out X-rays for exactly 47 minutes before shutting off abruptly. Is it a pulsar with an unusually slow spin, a binary system where one star's winds periodically ignite the other's magnetic field, or something entirely new? Theories abound, but the truth remains elusive, buried in data streams that astronomers are still untangling. What's clear is this: the Orion Nebula's X-ray portrait reveals a universe within a universe. Behind the serene facade of gas and starlight, there's a realm where matter is superheated to unimaginable temperatures, where magnetic fields tangle into knots of pure energy, and where the very processes that shape solar systems play out in bursts of invisible fury. It's a reminder that light is just one language the cosmos speaks, and sometimes the most astonishing stories are told in wavelengths our eyes will never see. The Orion Nebula might seem like the last place you'd expect to find water after all. This cosmic cauldron blasts its gas clouds with enough ultraviolet radiation to rip molecules apart. Yet hidden within its turbulent depths lies one of the universe's most surprising stockpiles, enough water vapor to fill Earth's oceans billions of times over. This isn't liquid water sloshing through space, it's a diffuse mist of molecules, each one forged in the frigid hearts of dust clouds where temperatures hover just above absolute zero. Here, in the shadows of the nebula's darkest lanes, oxygen atoms cling to hydrogen, forming water ice coatings thinner than a strand of DNA on every speck of cosmic dust. What makes this discovery so astonishing is the sheer scale. The Herschel Space Observatory detected water emissions so intense they revealed reservoirs stretching across light years, some concentrated in frigid stellar nurseries, others swirling in vast, invisible halos around newborn stars. In one particularly dense region, astronomers calculated over 5,000 times the water in all of Earth's oceans evaporating from a single protostar's disk, a phenomenon dubbed a steam engine by researchers. These molecules aren't passive bystanders, they're cosmic coolants. As water vapor radiates heat away into space, it helps collapsing gas clouds shed energy, accelerating the birth of new stars. It's a paradox. In the vacuum of space, water acts like a thermostat, quietly shaping the universe's stellar factories. But the real magic happens when radiation intervenes. When ultraviolet light from massive stars like Theta 1 Orionis C hits these ice-coated grains, the water doesn't just melt, it explodes. Molecules are blasted free in a process called photodesorption, creating shimmering halos of vapor around young stars. Some of this liberated water gets incorporated into forming planetary systems, possibly seeding future oceans on alien worlds. Other molecules are torn apart by radiation, their hydrogen and oxygen atoms recombining into unexpected compounds like hydrogen peroxide detected in the nebula's gas clouds as eerie spectral fingerprints. The most tantalizing clue lies in the water's isotopic signature. Earth's oceans contain a specific ratio of normal water to heavy water, where hydrogen is replaced by deuterium. The Orion Nebula's reservoirs show a strikingly similar mix, hinting that the ingredients for our planet's seas might have once floated in such stellar nurseries before being delivered by comets or icy asteroids. It's a humbling thought. The same processes brewing water in Orion's depths 400 trillion miles away could have filled the glass sitting on your table. Yet for all we've uncovered, mysteries remain. Why do some protostars swim in water vapor while others are parched? How do molecules survive the nebula's radiation onslaught long enough to reach planet-forming disks? Each answer pulls back another curtain on how the universe's most precious resource disperses and how often it might rain down on worlds beyond our own. The Orion Nebula's water isn't just a chemical curiosity. It's a trail of clues written in vapor, whispering secrets about how life's essential elements travel the stars. Deep in the Orion Nebula's frigid shadows, where temperatures plunge to -400 degrees Fahrenheit and dust clouds blot out starlight, an invisible alchemy is at work. Here, in the darkest crevices between stars, simple atoms collide and cling, forming molecules so complex they'd feel at home in a chemistry lab. Methanol, formaldehyde, even acetic acid, the same compound that gives vinegar its bite, all drift through the void, clinging to microscopic grains of dust like frost on a windowpane. These aren't random contaminants, they're the universe's first steps toward building the ingredients for life, forged in conditions so harsh they'd obliterate most earthly substances. Take methanol, for instance. This simple alcohol, detected in vast quantities across the nebula's cold clouds, forms when carbon monoxide gas freezes onto dust grains and reacts with hydrogen atoms. It sounds straightforward, but the process is anything but. Each reaction requires precise conditions, just the right temperature, just enough shielding from radiation, to prevent these fragile molecules from being torn apart by the nebula's harsh ultraviolet glare. Yet somehow, against all odds, they persist. The Atacama Large Millimeter Array has mapped methanol's distribution in stunning detail, revealing vast reservoirs where this organic compound swirls in concentrations thousands of times denser than anywhere else in interstellar space. Then there's formaldehyde, a molecule so reactive it's considered a building block for sugars like ribose, a key component of RNA. In the nebula's shielded pockets, it forms through a delicate dance of radiation and cold. Ultraviolet light breaks apart larger molecules, releasing fragments that recombine into new configurations on icy grain surfaces. What's startling isn't just its presence, but its abundance. Some filaments contain enough formaldehyde to manufacture billions of copies of every gene in the human genome, all floating in the cosmic dark. But the real showstopper, glycine, the simplest amino acid and a fundamental piece of life's protein-building toolkit. While its detection in the Orion Nebula remains debated, tentative signals in radio spectra suggest it might be lurking there, clinging to dust grains alongside its chemical cousins. If confirmed, it would mean the universe isn't just making alcohols and sugars in Orion, it's assembling the very alphabet of biology. Here's what's truly mind-bending. These molecules shouldn't survive the nebula's radiation bath. Yet they do, sheltered in the densest knots of gas or shielded by layers of frozen carbon monoxide that act like cosmic sunscreen. Even more astonishing is their mobility. When newborn stars heat nearby ice, these organics sublimate, transitioning directly from solid to gas, and hitch rides on stellar winds, potentially sprinkling their complexity across young planetary systems. The implications ripple far beyond Orion. These molecules are proof that the universe operates as a vast, patient chemist, given enough time and the right conditions. A protective dust cloud here, a sheltered ice grain there, it can assemble increasingly complex compounds through processes we're only beginning to map. And if it's happening here in this one nebula, it's likely happening everywhere the cosmos provides similar refuge. Perhaps most poetic is the timescale. The methanol and formaldehyde we detect today may have formed millions of years ago, their molecules preserved in deep freeze until a passing shockwave or protostar's warmth nudged them back into the gas phase where our telescopes could find them. They're messages in bottles drifting through time, waiting to tell us how chemistry bridges the gap between stardust and life. The Orion Nebula's organic molecules don't just hint at life's potential elsewhere in the universe. They force us to reconsider life's inevitability. If such complexity arises naturally in stellar nurseries, then the transition from chemistry to biology might not be a fluke, but a cosmic imperative written into the fabric of star-forming clouds themselves. And somewhere in that swirling maelstrom of gas and dust, the same processes that built these molecules could be crafting others we've yet to discover, each one a stepping stone across the universe's grand experiment. Hidden among the Orion Nebula's glittering tapestry of stars, some celestial performers refuse to follow the script. These aren't your typical steady beacons, they're cosmic strobe lights, flickering erratically with no discernible rhythm. Astronomers call them variable stars, but that clinical term hardly captures their bizarre behavior. One might dim by half its brightness overnight, while another suddenly flares to 10 times its normal luminosity for no apparent reason. These aren't software glitches or telescope errors, they're real, violent transformations playing out across light years, challenging our understanding of stellar mechanics. Take V380 Orionis, a young star nestled near the Trapezium Cluster. Most days it shines with the consistency of a street lamp, but over decades of observations, astronomers have caught it suddenly plunging into near darkness for weeks at a time, only to rebound just as abruptly. The leading theory, a colossal warp in its protoplanetary disk, a dusty frisbee of debris 10 times wider than our solar system that periodically eclipses the star as it rotates. Imagine a record spinning on a turntable, but with a mountain-sized warp that swings into view every few years, blotting out the central light. The sheer scale is mind-bending. That warp would tower high enough to swallow Jupiter's orbit whole. Yet eclipses can't explain all these stellar mood swings. Some variables, like NV Orionis, flicker due to magnetic tantrums that would make our sun's solar flares look like candle flickers. These stars are cosmic electromagnets, their surfaces crisscrossed by magnetic fields strong enough to distort atoms. When these fields snap and reconnect, a process called magnetic reconnection, they unleash explosions visible across interstellar space. The aftermath, starspots larger than the Sun's entire surface, and coronal loops so hot they glow in X-rays. Then there's the mystery of the slow dippers, stars like UX Orionis that fade gradually over months before brightening again. These aren't simple eclipses. Their light curves show complex, jagged dips suggesting swarms of dust clumps orbiting in chaotic swarms. Some researchers propose these are planetesimals colliding and shattering near the star, creating temporary dust clouds that dim the light. Others suspect massive cyclones of gas, stirred up by gravitational interactions with unseen companions. The most perplexing cases defy all categories. Stars that brighten asymmetrically as if something's glowing intensely on just one hemisphere. Objects that flicker in unrelated wavelengths, simultaneously visible light dimming while infrared spikes. Each anomaly is a clue hinting at processes we've yet to imagine. What makes Orion's variables particularly valuable is their youth. Unlike mature variable stars elsewhere, these are stellar toddlers still figuring out their equilibrium. Watching their antics is like catching a kindergarten class mid-tantrum chaotic, but revealing fundamental truths about how stars grow up. Every erratic pulse, every unexplained dimming, is a piece in the grand puzzle of stellar adolescence, a phase our own sun likely went through billions of years ago. In a nebula already overflowing with wonders, these capricious stars remind us that even the most fundamental cosmic objects still hold surprises. Their misbehavior isn't just noise, it's data, written in the language of flickering light, waiting to be decoded. And with every strange new light curve they paint across our telescopes, they prove that in the Orion Nebula, the only constant is change. At first glance, the Orion Nebula seems to glow uniformly, a radiant cloud where starlight diffuses evenly through gas. But tilt the cosmic lens just right, and an extraordinary spectacle emerges. Shadows stretching for trillions of miles, cast not by solid objects, but by veils of dust so fine they behave like celestial theater scrims. These aren't mere absences of light, they're dynamic sculptures carved by the interplay of raw starlight and primordial soot, the most striking example. The dark sword, a shadow so crisp, its edges reveal the microscopic structure of dust grains lining an otherwise invisible filament. When Theta 1 Orionis sees brutal radiation hits this tendril, the dust doesn't just block light, it sculpts it, projecting a silhouette 15 times longer than our solar system onto the nebula's glowing backdrop. What makes these shadows so baffling is their precision. In Earth's atmosphere, light diffuses around obstacles, blurring shadow edges. But in the near-perfect vacuum of space, there's no air to scatter photons. So when dust lanes drift in front of bright gas clouds, they cast knife-sharp profiles. Hubble's images capture this eerie clarity. Tendrils with feathery branches, knots that resemble clenched fists, even helical spirals twisting like DNA strands, all rendered in negative space. Some shadows even reveal motion. Time-lapse observations show subtle shifts over decades, proving these dust structures aren't static. They writhe, stretched by magnetic fields or buffeted by stellar winds, their slow dance chronicled in creeping silhouettes. Yet the real magic happens when shadows interact with the nebula's 3D architecture. A single dust filament might cast multiple overlapping shadows, each layer filtering starlight differently. Near-infrared cameras pierce this complexity, showing how longer wavelengths slip around dust grains that block visible light. The result, a shadow puppet show on cosmic steroids, where the same structure appears solid in optical light but ghostly transparent in infrared. In one stunning case, two shadows intersect at just the right angle to create a natural pinhole camera, projecting an inverted image of the Trapezium Cluster onto a distant gas wall, a perfect miniature of the stars themselves. The most haunting shadows aren't cast by dust at all, but by ionized gas. When ultraviolet radiation strips electrons from hydrogen atoms, the resulting plasma becomes opaque to certain wavelengths. These ionization shadows create voids where background starlight vanishes abruptly, as if someone flipped a switch. One such shadow near the Orion Bar spans 3 light-years, its edges fluorescing where radiation slams into neutral gas, a glowing outline of an invisible phenomenon. These plays of light and dark aren't just celestial eye candy. They're diagnostic tools allowing astronomers to map the nebula's hidden skeleton. By analyzing shadow shapes, scientists can deduce dust grain sizes typically microscopic like smoke particles, and even their composition often carbon-rich with icy coatings. Some shadows flicker as background stars vary in brightness, acting like natural X-ray machines that reveal denser clumps. Others betray the presence of unseen objects, protoplanetary disks or brown dwarfs, that leave telltale dips in the light passing behind them. Perhaps the most poetic lesson lies in the shadow's impermanence. Unlike the static silhouettes of moon craters or planetary rings, Orion's shadows are fleeting. The same radiation that illuminates them also erodes their casters, evaporating dust grains atom by atom. Within millennia, today's dramatic profiles will dissipate, replaced by new configurations as the nebula evolves. For now, they stand as reminders. Even in the brightest corners of the cosmos, darkness isn't empty. It's alive with structure, a temporary art exhibit written in negative space, waiting for its next act. The Orion Nebula isn't just a static painting of gas and starlight. It's a cosmic demolition derby, where high-speed collisions etch glowing scars across the void. Among the most striking are the bow shocks, razor-thin arcs of plasma that glow like celestial fingerprints, each one marking the spot where a star's hurricane-force winds slam into slower-moving gas. Picture a speedboat tearing across a lake, its prow pushing water into a V-shaped wake. Only here, the boat is a star, and the water is interstellar material being compressed and heated to millions of degrees. These aren't gentle ripples, they're the nebula's equivalent of sonic booms, shockwaves so intense they make fighter jets breaking the sound barrier look sluggish by comparison. Take the bow shock around the runaway star Eerie, which streaks through Orion's outskirts at 80,000 miles per hour. Its crescent-shaped shock front spans half a light-year, glowing electric blue as it rams into surrounding hydrogen. What's mesmerizing isn't just its speed, it's the physics unfolding at the edge. As particles collide, they don't just bounce, they're accelerated to near-light speeds, emitting synchrotron radiation that paints the shock in X-rays. The finer details, they're even wilder. Hubble's close-ups reveal tiny, finger-like filaments along the arc turbulence frozen in time, where eddies and whirlpools churn at the boundary between the stellar wind and the nebula's resistance. But Eerie's shock is just one flavor in Orion's menagerie. Some bows, like those around the massive star Theta 2 Orionis, pulse rhythmically as their parent star's winds intensify and wane. Others, like the bizarre double bow of LL Orionis, show nested arcs, evidence of sporadic outbursts where the star belched material in fits and starts. The most mysterious are the headless shocks where the driving star is nowhere to be found. These phantom arcs, unmoored from any visible source, might trace the paths of dead or dying stars whose winds persist even after their demise. The real puzzle, bow shocks defy expectations. According to models, many should dissipate quickly as they plow through the nebula's uneven gas. Yet some persist for millennia, their shapes too crisp, their glow too bright. The secret might lie in magnetic fields. Threading through the shock fronts like invisible rebar, these fields could stabilize the structures, preventing them from shredding apart. Radio observations have spotted telltale polarization patterns that support this evidence of charged particles spiraling along magnetic lines, reinforcing the shock like cosmic stitching. Beyond their beauty, these structures are cosmic breadcrumbs. By mapping their curves, astronomers can reconstruct the motions of stars that carved them, including some now long gone. There are also laboratories for extreme physics, places where matter is compressed to densities found nowhere else in the nebula, sparking chemical reactions that might forge complex molecules. And in their glowing arcs, we might even glimpse our own sun's past. 4.5 billion years ago, as our newborn star toddled through its natal cluster, it too likely trailed a bow shock, one that faded as the solar system drifted into quieter galactic suburbs. The nebula's bow shocks remind us that nothing in space stands still. Every gleaming arc is a snapshot of violence, a temporary monument to the forces that shape stellar nurseries. And as they flare and fade, they whisper a universal truth. In the cosmos, even the gentlest breeze is a supersonic gale in disguise. Threading through the Orion Nebula like invisible puppet strings, vast magnetic filaments shape the chaos with an unseen hand. These aren't the nebula's glowing gas tendrils or dark dust lanes, they're colossal force fields, stretching for light years, their presence revealed only by the way they drag charged particles into alignment. Radio telescopes like the Atacama Large Millimeter Array have mapped these structures in stunning detail, catching dust grains behaving like compass needles, all pointing the same direction, a telltale sign of magnetic influence. The sheer scale is staggering. Some filaments wield fields thousands of times stronger than Earth's, powerful enough to defy the nebula's turbulent winds and sculpt gas into eerie, orderly strands. What's mesmerizing isn't just their strength, it's their structure. Unlike the tangled mess we'd expect in such a violent environment, these magnetic lines often run startlingly straight, as if the universe pressed them with an iron. In the Orion Molecular Cloud 1, filaments align like railroad tracks across 15 light-years, guiding collapsing gas into star-forming knots like beads on a wire. Elsewhere, they spiral into helical coils, wrapping around protostellar jets like DNA strands. The most bizarre twist, some filaments appear braided, their magnetic lines twisted into cosmic ropes that channel energy across the nebula like high-voltage power lines. The origins of these magnetic monsters remain hotly debated. One theory suggests they're fossil relics, fields frozen into the gas when the nebula first formed, amplified as gravity compressed the cloud. Others propose dynamo effects where swirling plasma currents generate new fields like a cosmic generator. The wild card, supernova shocks. When massive stars die, their explosions might ripple through the nebula, stretching and combing magnetic lines into these precise configurations, like a cosmic comb dragging through the fabric of space itself. But the real magic lies in what these filaments do. In regions where gas should be too diffused to collapse into stars, magnetic fields act like cosmic scaffolding, propping up gas clouds against gravity's whisper. They funnel material along their lengths, creating dense hubs where protostars ignite. They even govern stellar spin. Young stars entangled in magnetic filaments rotate slower than expected, as if the fields are cosmic brake pads. Without them, the nebula might be a shapeless fog, its star-forming efficiency slashed to a fraction. The most haunting evidence comes from polarized light. As dust grains align with magnetic fields, they scatter light in predictable patterns, a phenomenon ALMA exploits to map the invisible. These observations reveal fields so organized they resemble the structured fibers of a muscle, flexing and adjusting as the nebula evolves. Some regions show conflicting field directions, where magnetic domains clash in slow-motion battles that might one day spark new bursts of star formation. Yet for all their power, these filaments are ephemeral. Over millennia, the very stars they help birth will erode them, their radiation ionizing gas, their winds tearing at the field's delicate balance. It's a cosmic irony. Magnetism shapes stellar birth, only to be undone by its creations. For now, though, these hidden architects remain at work, weaving order from chaos, one invisible thread at a time, proof that even in the universe's most riotous nurseries, there's a method to the madness. Beneath the Orion Nebula's blazing stellar spectacle lies a haunting underworld of faint, ghostly glows, ethereal emissions so subtle, they're often washed out by the nebula's radiant fireworks. These aren't the vibrant pinks and greens of ionized hydrogen or oxygen. They're the whispers of gas so tenuous their light registers as little more than a cosmic afterglow. But dismiss them as background noise, and you'd miss one of the nebula's most profound secrets, a delicate lattice of energy woven through the void by processes we're only beginning to decode. Take the nebula's so-called extended red emission, a mysterious crimson haze first spotted in the 1980s. Unlike the sharp spectral lines of hydrogen or nitrogen, this glow is broad and diffuse, like someone smeared watercolor across the cosmos. Its source, tiny nanoscale particles, likely carbon-rich dust grains excited by the Trapezium Cluster's ultraviolet onslaught. As these microscopic flecks absorb high-energy photons, they re-emit the energy at longer, redder wavelengths, painting the nebula's outskirts with a surreal, sunset-like sheen. What's eerie isn't just the color, it's the distribution. This red glow clings to the nebula's darkest corners, illuminating regions where traditional emission lines fade to nothing. It's as if the dust itself is fluorescing, revealing hidden structures invisible to other wavelengths. Then there's the Orion Veil, a vast bubble-like shell of ionized gas stretching far beyond the nebula's core. Visible only through narrowband filters that isolate its faint emissions, this structure glows with the soft blue of doubly ionized oxygen, but at temperatures and densities so low it defies conventional models. The veil isn't a single entity, it's a fractal network of filaments, each one tracing the paths of ancient stellar winds or supernova shocks that swept through the nebula millions of years ago. Some filaments pulse with strange periodicities, their brightness flickering as if something, perhaps unseen magnetic waves, is vibrating them like plucked guitar strings. The most enigmatic glow of all, the cosmic green corridor. While the nebula's famous green oxygen emission dominates its core, a fainter version of this hue extends in tendrils far into the surrounding molecular cloud. Unlike its brighter counterpart, this emission isn't confined to ionized regions. It seeps into neutral hydrogen zones, suggesting a rogue process, perhaps collisions between electrons and metastable oxygen atoms, is at work. The effect is spectral, a luminescent maze guiding lost starlight through the nebula's labyrinthine depths. What makes these ghostly glows so invaluable is their diagnostic power. While the nebula's bright hotspots scream for attention, these faint emissions chronicle quieter, but no less critical, phenomena. The extended red emission maps the distribution of interstellar dust, the very particles that shield budding solar systems from lethal radiation. The veil's filaments encode the nebula's violent history, its shocks and outflows frozen in plasma, and the green corridor, it might hold clues to how energy propagates through the interstellar medium, a puzzle central to understanding star formation across the universe. In their subtlety, these glows remind us that the cosmos speaks in more than shouts. Sometimes its most profound truths arrive as murmurs, faint, patient, and waiting for those willing to listen closely. And in the Orion Nebula, where light so often overwhelms, it's the whispers that may yet tell the fullest story. At first glance, the Orion Nebula's dust might seem like simple cosmic debris, a hazy afterthought to its dazzling stars and glowing gas. But zoom in closer, and this unassuming dust reveals itself as one of the nebula's most sophisticated architects. Unlike the uniform soot of a fireplace, it's a meticulously crafted cocktail of silicates and carbon-rich grains, each type playing a distinct role in shaping the nebula's light, structure, and even its potential for fostering life. These particles are staggeringly small, most no larger than a wavelength of visible light, yet their collective influence is so profound, they dictate how we see the nebula from Earth. Silicates, the same minerals that make up Earth's sand and rocks, dominate the mix, In the nebula's cold molecular clouds, they form jagged, irregular shapes, their surfaces pocked by centuries of bombardment from cosmic rays and ultraviolet radiation. When starlight hits these grains, they scatter blue wavelengths more efficiently than red, the same reason our sky appears blue. That's why the nebula's brightest regions often shimmer with an ethereal azure glow, as if lit from within. But venture deeper into the dust lanes, where grains clump into thicker clouds and the light scattering becomes more complex. Here, multiple layers of silicates act like a cosmic colander, filtering out shorter wavelengths entirely until only deep reds and infrareds remain. This selective filtering creates the nebula's dramatic contrast, inky-black tendrils set against radiant pink hydrogen clouds. Then there's the carbon faction. Unlike silicates, these grains are smoother and darker, built from chains of carbon atoms that absorb rather than scatter light. Some resemble microscopic tar balls forged in the atmospheres of aging stars before being expelled into space. Others, known as polycyclic aromatic hydrocarbons (PAR), are flat, plate-like molecules that fluoresce when struck by ultraviolet radiation, adding a faint, ghostly glow to the nebula's darker recesses. These carbon compounds are cosmic sponges, soaking up harsh radiation that would otherwise break apart delicate molecules, acting as natural shields for the chemical processes that might one day lead to life. The real magic happens when these two dust types collide literally. In the turbulent maelstrom of the nebula, silicate and carbon grains constantly bump into one another, their surfaces becoming sticky with icy coatings of water, methanol, and other volatiles. These ices aren't just passive frost, they're chemical laboratories where simple molecules link into more complex ones. When a stray ultraviolet photon hits these icy mantles, it can trigger reactions that form precursors to amino acids or sugars, building blocks that might eventually seed new planetary systems. But the dust's piece de resistance is how it shapes the nebula's very appearance from our vantage point. Because the grains are slightly elongated, they tend to align with the nebula's magnetic fields like compass needles in syrup. This alignment polarizes the starlight passing through them, creating subtle patterns detectable with specialized telescopes. By mapping these patterns, astronomers have reconstructed the nebula's hidden magnetic skeleton, invisible lines of force that sculpt star-forming regions and steer the paths of newborn stars. Perhaps most astonishing is the dust's longevity. These grains shouldn't survive the Trapezium Cluster's relentless radiation, which should vaporize them within centuries. Yet they persist, replenished by an invisible conveyor belt of destruction and renewal. As massive stars die, they spew fresh silicates and carbon into the void, while supernova shocks forge new grains in their aftermath. It's a cycle as old as the galaxy itself, one that ensures the Orion Nebula's dust will continue painting its masterpiece across the cosmos, long after its brightest stars have burned out. Far from being mere space dirt, this dust is the nebula's unsung artist, its silent chemist, and its cosmic shield, all rolled into motes smaller than a speck of pollen. And every time we gaze at Orion's glowing tapestry, we're seeing their handiwork, a universe rendered in starlight and shadow, one grain at a time. One of the Orion Nebula's most perplexing puzzles isn't written in glowing gas or swirling dust, it's etched in starlight itself. Scattered among the nebula's infant stars are celestial anomalies that shouldn't exist. Mature, middle-aged suns that appear millions of years older than the nebula's estimated age of just 1 million years. It's like finding grandparents in a kindergarten classroom, a cosmic contradiction that forces astronomers to rethink everything they know about stellar nurseries. Take HD 36917, a star so evolved it's already left its main sequence phase, yet sits squarely within the nebula's bustling core. Its spectrum reveals advanced nuclear burning signatures, elements like lithium nearly depleted, a telltale sign of stellar maturity. Based on standard models, this star should have formed at least 5 million years ago, long before the nebula's current gas clouds even collapsed. Then there's the B-type stars in Orion's outskirts, their surfaces littered with fusion byproducts that typically take 10 million years to accumulate. These aren't isolated cases. Nearly 10% of the nebula's stellar population shows similar age discrepancies, creating a timeline that simply doesn't add up. So how did these time-traveling stars get here? One radical theory suggests the Orion Nebula isn't a single, cohesive nursery, but a layered graveyard of multiple star-forming epochs. Imagine a cosmic palimpsest where new stars ignite atop the ashes of older generations. Supernova from an ancient cluster could have compressed surrounding gas, triggering fresh rounds of star formation while preserving leftover stars from the previous wave. Infrared surveys lend credence to this idea, revealing ghostly shells of dust that might mark the boundaries of these extinct bubbles, another possibility. Stellar immigration. Like celestial nomads, older stars might have drifted into the nebula from neighboring regions, lured by gravity's pull. The Orion Complex, a sprawling network of gas clouds spanning hundreds of light years, contains several subregions with varying ages. Turbulent interactions between these zones could have flung mature stars into the younger nebula, where they now masquerade as members of the brood. Proper motion studies show a handful of these outliers racing along trajectories that trace back to older clusters like NGC 1981, supporting the interstellar Hitchhiker hypothesis. But the most tantalizing explanation challenges the very way we measure stellar ages. Traditionally, astronomers gauge a star's maturity by its temperature, brightness, and chemical makeup, but these metrics assume stars form in isolation. New simulations show that in dense clusters like Orion's core, chaotic gravitational interactions can accelerate stellar evolution. Stars might steal mass from neighbors, merge in violent collisions, or spin so fast from close encounters that their internal nuclear processes go into overdrive. The result, a star that looks middle-aged by all standard tests, but is actually a precocious toddler running on cosmic adrenaline. This age paradox isn't just academic, it reverberates through our understanding of galactic evolution. If stars can appear artificially old, then dating distant clusters becomes fraught with uncertainty. If nebulae harbor multiple generations, then planetary systems might form amid the gravitational wreckage of dead stars, seeding worlds with heavy elements far sooner than expected. And if stellar ages aren't the reliable clocks we thought, then the universe's timeline of star formation might need rewriting. The Orion Nebula, it seems, is more than a nursery. It's a celestial melting pot where time itself becomes fluid. And tucked within its glowing folds, those enigmatic older stars stand as silent witnesses to processes we're only beginning to unravel. The Orion Nebula won't always blaze with its current brilliance. It's a cosmic masterpiece with an expiration date. Over the next million years, the very forces that sculpted its beauty will tear it apart. The Trapezium Cluster's most massive stars are ticking time bombs. Their ultraviolet radiation and supersonic winds already erode the surrounding gas at a staggering rate. Every second, they strip away enough material to build 1,000 Earths, carving ever wider cavities in the nebula's heart. But the real destruction hasn't even begun. Stars like Theta 1 Orionis C, those colossal blue giants, live fast and die violently. Within a few 100,000 years, they'll detonate as supernova, their shockwaves ripping through the nebula like cosmic tsunamis, hurling entire gas clouds into interstellar space. This dispersal won't be random. Simulations show the nebula's structure will dictate its unraveling. Dense pillars like the fingers might stubbornly cling to existence for another million years, while wispy filaments vanish almost overnight. The nebula's intricate magnetic fields, now holding everything together, will become agents of chaos, channeling supernova energy into focused jets that punch holes through remaining gas pockets. Even the dark lanes, those dust-rich sanctuaries for complex molecules, will evaporate, their icy grains blasted into vapor by successive stellar explosions. What emerges from this turmoil won't be emptiness, it'll be a glittering open cluster, something resembling the Pleiades. The trapezium stars, having long since scattered, will drift apart at leisurely speeds, maybe a few kilometers per second, carrying their planets, if any survived, into the galactic suburbs. The nebula's quieter stars, the red dwarfs and Sun-like G-types, will outlast their brilliant siblings, orbiting a common center of gravity that weakens with each passing eon. Over hundreds of millions of years, even this loose association will dissolve, its members becoming field stars adrift in the Milky Way's spiral arms. Yet traces of the nebula's legacy will endure. Heavy elements forged in its core, carbon, oxygen, iron, now suffuse the expelled gas, enriching future stellar nurseries. Some of the youngest stars, those still cocooned in evaporating Proplyds when the end comes, might retain dust-rich debris disks long enough to form rocky worlds. And those bizarre runaway stars, their high-velocity journeys will seed other regions with Orion's distinctive chemical fingerprints, like cosmic graffiti artists tagging the galaxy. The most poetic fate belongs to the nebula's smallest survivors, brown dwarfs and rogue planets. Too faint to attract attention, these cast-offs will drift through interstellar space for trillions of years, outliving not just their birthplace but most stars in the universe. Some might even carry frozen remnants of the nebula's organic molecules, amino acids, sugars, or more complex compounds preserved in their icy mantles like time capsules from a lost era. Future astronomers, whether human or otherwise, might piece together Orion's story from these scattered clues. The cluster's stars will share telltale motion vectors, all pointing back to a convergent origin. Their metallicity profiles will reveal a shared birthplace rich in supernova debris. But the glowing gas itself, the radiant tapestry we see today, it'll be long gone, its atoms recycled into new stars, planets, or perhaps, on at least one world we know of, into beings who gaze skyward and wonder about the nursery their sun once called home. The Orion Nebula isn't just a static painting of celestial beauty, it's a maelstrom of cosmic weather so violent, it makes Earth's worst hurricanes look like gentle breezes. Imagine winds that don't whisper but scream at thousands of kilometers per second, where gas swirls in towering supercell-like updrafts, and shockwaves ripple through the void like thunder without sound. This isn't metaphor, it's the reality of a nebula where the atmosphere is a churning ocean of ionized plasma, sculpted by forces we're only beginning to understand. At the heart of this chaos are the trapezium stars, acting like celestial jet streams. Their ultraviolet radiation doesn't just illuminate the nebula, it superheats the gas, creating pressure differentials that launch supersonic winds. These aren't the steady, predictable flows of a planetary weather system. They're erratic gusts, surging and collapsing as magnetic fields twist them into knots. Near Theta 1 Orionis C, winds have been clocked at over 2,000 kilometers per second, fast enough to cross the continental United States in the blink of an eye. Where these gales collide with cooler gas, they spawn turbulent eddies visible in Hubble images as ghostly whirlpools, some large enough to swallow our solar system whole. The nebulous storms leave unmistakable fingerprints. In its eastern quadrant, astronomers have mapped a structure nicknamed the whirlwind, a vortex of gas stretching 3 light-years across. Its spiral arms aren't static, they writhe like living things, their motion betraying hidden forces beneath. Some researchers believe this is the nebula's version of a cyclone, fueled by energy from a cluster of young stars buried in its core. Others argue it's a Kelvin-Helmholtz instability, a cosmic version of waves crashing in a choppy sea, where faster-moving gas shears against slower layers, creating those eerie curls. But the real spectacle unfolds at microscopic scales. As these galactic gales tear through the nebula, they don't just move gas, they torture it. Atoms are stripped of electrons, molecules are ripped apart, and dust grains are sent careening like shrapnel. The result, a form of interstellar hail, microscopic pellets of silicate and carbon, battered by winds until their surfaces are pockmarked like golf balls. Some grains become electrically charged, turning them into cosmic pinballs zipping along magnetic field lines. Others clump together in the turbulent equivalent of calm eyes, forming the seeds of future planets. What's most astonishing is how this violence creates order. The same winds that shred gas clouds also compress them, triggering chain reactions of star formation. In the nebula's quiet zones, areas sheltered behind dense dust lanes, turbulence dies down just enough for gravity to take over, pulling gas into protostellar cores. It's a delicate balance. Too much chaos and stars can't form, too little and the gas remains diffuse. The Orion Nebula walks this tightrope with cosmic precision, its weather acting as both destroyer and architect. Yet for all we've decoded, mysteries linger. Why do some regions exhibit fractal-like turbulence with patterns repeating at every scale, while others resemble chaotic froth? How do magnetic fields, woven through the gas like invisible threads, stabilize some storms while amplifying others? Every answer peeled back reveals new questions, reminding us that even in our cosmic backyard, the universe's most ordinary phenomena harbor layers of complexity we've only begun to scratch. This isn't just weather, it's the engine of creation itself, where the same forces that ravage also nurture. And as we watch these tempests play out across light years, we're glimpsing the dynamic, ever-changing heartbeat of stellar birth. The Orion Nebula doesn't just host stars, it forges them in the furnace of its own eternal storm. Among the Orion Nebula's glittering stars and luminous gas, the most intriguing actors might be the ones we can't see at all. Hidden beneath veils of dust and lurking in the cold shadows between stars, an entire population of cosmic ghosts, rogue planets, failed stars, and other enigmatic objects could be waiting for discovery. These aren't just theoretical speculations, their presence is betrayed by the nebula's subtle gravitational whispers, the way stars wobble inexplicably or gas clouds ripple as if tugged by unseen hands. If the Orion Nebula is a bustling city, these hidden residents are its undocumented inhabitants, shaping the neighborhood from behind the scenes. Take rogue planets, worlds untethered to any star, drifting through the nebula's chaos like interstellar vagabonds. Some might be frozen wastelands, exiled from their birth systems by gravitational upheavals. Others could be steam planets, still warm from their violent ejections, their atmospheres glowing faintly in infrared. A handful might even harbor subsurface oceans, kept liquid by tidal forces or radioactive decay, making them dark, wandering candidates for exotic life. The Hubble and James Webb telescopes have glimpsed hints of these nomads' thermal anomalies moving too slowly to be stars, yet too large to be asteroids. But confirming their existence requires catching their faint thermal glow against the nebula's radiant backdrop, like spotting a candle flickering in front of a floodlight. Then there are brown dwarf stellar failures, too massive to be planets yet too small to ignite hydrogen fusion. These cosmic in-betweeners smolder at temperatures barely hotter than a campfire, their dim glow drowned out by the nebula's brilliance. Yet their gravity leaves fingerprints. Some of the nebula's gas filaments move with unexpected sluggishness, as if weighted down by invisible anchors. A few protoplanetary disks exhibit bizarre warps, their shapes distorted by the pull of unseen companions. One tantalizing candidate, lurking near the Orion Bar, was detected solely by its gravitational microlensing effect, a fleeting dimming of a background star as the dwarf passed in front. But the most elusive quarry might be black holes, not the supermassive giants at galactic centers, but smaller, stellar mass remnants hiding in plain sight. Simulations suggest the nebula's violent stellar environment should have produced several of these gravitational traps, their presence betrayed only by the occasional X-ray flare as they snack on stray gas. One mysterious X-ray source, designated Orion X1, flickers erratically near the Trapezium Cluster, its emissions too intense for a neutron star yet too faint for a typical black hole. Could it be a rare intermediate mass black hole or something even stranger? The real challenge in hunting these phantoms is separating their signals from the nebula's cacophony. Advanced algorithms now sift through decades of data, looking for statistical anomalies, slight stellar motions that don't fit predictions, or heat signatures that vanish when viewed at different wavelengths. The upcoming Nancy Grace Roman Space Telescope, with its unprecedented wide-field infrared vision, might finally lift the veil, capturing the feeble heat of rogue planets or the subtle lensing effects of brown dwarfs. What's at stake isn't just a census of hidden objects, it's a fundamental rewrite of how we understand star formation. If the nebula conceals legions of rogue planets, it suggests solar systems are far more fragile than we thought, with planets routinely cast adrift. A population of brown dwarfs could mean stellar formation has a minimum size, a cutoff point below which nature refuses to make true stars and lurking black holes. They'd be evidence of a violent past where the nebula's earliest generations of stars lived fast, died young, and left behind dark skeletons. The Orion Nebula's unseen residents are more than cosmic clutter. They're missing puzzle pieces in our understanding of stellar ecology. Every one we find forces us to redraw the map, to acknowledge that what we see is only a fraction of what's truly there. And as technology sharpens our vision, who knows what other ghosts might emerge from the shadows, rewriting the nebula's story one discovery at a time. From the gravitational mosh pit of the Trapezium Cluster to the phantom whispers of rogue planets, the Orion Nebula isn't just a cosmic wonder, it's a living laboratory of the bizarre. We've journeyed through 30 of its strangest phenomena, each one defying expectations. Stars firing corkscrew jets like celestial artillery, magnetic filaments braiding the void into invisible sculptures, and explosions so violent they're still ringing across the nebula centuries later. We've watched shadows stretch trillions of miles from dust grains no larger than smoke particles, witnessed water molecules forming in the harshest vacuum, and stumbled upon stellar runaways fleeing their birthplace at breakneck speeds. But here's the humbling truth: every answer uncovers new questions. Why do some protoplanetary disks spiral like cosmic pinwheels while others shatter into fragments? What dark architects shaped the nebula's ghostly infrared halos, and just how many hidden black holes or failed stars lurk in the uncharted depths? The Orion Nebula refuses to be pinned down. Just when we think we understand its rhythms, it throws another curveball, an unexplained X-ray pulse, a molecule that shouldn't survive the radiation, or a star aging far too quickly. This cosmic tapestry isn't just a spectacle, it's a mirror. The same chaos birthing stars here likely sculpted our own solar system 4.5 billion years ago. Those organic molecules brewing in dark lanes, they're the precursors to life's building blocks. The violent stellar winds and explosions, they're the universe's way of scattering heavy elements that one day became planets, oceans, and even us. So what's next? With telescopes like James Webb peering deeper into the nebula's shadows and algorithms sifting through decades of data, we're on the brink of revelations that could rewrite astrophysics. Maybe we'll catch a black hole mid-meal or spot the first hints of life's ingredients assembling on a distant protoplanet. The Orion Nebula has spent centuries dazzling observers, from Galileo's first sketches to Hubble's iconic portraits, and it's not done yet. Now it's your turn. Which of these phenomena left you awestruck? What mysteries do you think will unravel next? Drop your thoughts below, because the universe's greatest stories aren't just written in starlight. They're written in curiosity, and yours might just inspire the next big discovery. The cosmos is listening.